Hi, it's Miss Roman, and we are going to review for your test this week covering Chapter 10. So this unit is over just photosynthesis, but it's still easy to confuse this information with the information about cellular respiration on last week's test. Now, photosynthesis is very important for two reasons. You probably know that photosynthesis is important because of the light energy, which is converted into chemical energy. But a lot of students don't know that photosynthesis is also important because it provides a new source of organic carbon. We learned several weeks ago that living organisms have a lot of organic molecules in common. We call those the macromolecules. They were nucleic acids, proteins, lipids, and carbohydrates. All of those are made up of organic molecules, and that means that they have a lot of carbon atoms in them. And as organisms live and pass away, some of these building blocks of the macromolecules are put back into circulation. However, a lot of the organic material is really just buried in the ground, and millions of years later, it is a fossil fuel. And if we did not have a new source of organic carbon to replace the organic carbon, which will end up becoming our fossil fuels, then life on this planet would begin to decrease. So photosynthesis can take carbon from carbon dioxide, which is an inorganic molecule, and then add that carbon onto an organic molecule to make these organic molecules larger and larger. So photosynthesis does two things. It gives us a new source of energy, and it gives us a new source of carbon. To understand photosynthesis, we have to review what the electromagnetic spectrum is and what light is. You've probably learned about light and the electromagnetic spectrum, maybe in lower school, definitely in middle school, and then you probably learned a little bit in physics and chemistry your freshman and sophomore year. And we're going to watch a short video, which is a review.
Light is the connection between us and the universe. Through light, we can experience distant stars and look back at the beginning of existence itself. But what is light? In a nutshell, light is the smallest quantity of energy that can be transported, a photon, an elementary particle without a real size that can't be split, only created or destroyed. Light also has a wave-particle duality, being kind of a particle and a wave at the same time, although this is a lie. Also, when we say light, we actually mean visible light, which is a tiny part of the electromagnetic spectrum, energy in form of electromagnetic radiation. Electromagnetic radiation consists of an enormous range of wavelengths and frequencies. Gamma rays have the smallest wavelengths because they're the highest energy photons, but most gamma rays are just under 10 picometers, which is still way smaller than a hydrogen atom. For reference, a hydrogen atom compared to a cent is about as big as a cent compared to the moon. Visible light is in the middle of the spectrum, in the range of about 400 nanometers to 700 nanometers, about the size of bacteria. On the other end of the spectrum, radio waves can be up to 100 kilometers in diameter, while the biggest wavelengths we know exist can span from 10,000 kilometers to a baffling 100,000 kilometers, way larger than Earth. From a physics standpoint, all these different waves are the same. They all have the wave-particle duality and travel at c, the speed of light, just at different frequencies. So what makes visible light special then? Well, absolutely nothing. We just happen to have evolved eyes that are good at registering exactly this part of the electromagnetic spectrum. This is not a complete coincidence, though. Visible light is the only set of electromagnetic radiation that propagates well in water, which happens to be where most eyes first evolved millions of years ago. That was a smart move because light not only interacts with matter, it's also altered by it and can be used to gather information about the world around us with almost no delay, which is arguably really helpful for survival. Okay, where does light come from? A vast range of electromagnetic waves are created when atoms or molecules drop from a higher state of energy to a lower one. They lose energy and emit it in the form of radiation. At the microscopic level, visible light is created when an electron within an atom that is in an excited state drops to a lower energy state and loses this excess energy. The same way incoming light can elevate an electron to a higher state of energy by being absorbed by it. Macroscopically, the moving charge of the electron creates an oscillating magnet field, which creates an oscillating electric field perpendicular to it. These two fields move themselves through space, transferring energy from one place to another, carrying information about its place of creation with it. Why, of all the things in the universe, is light the fastest thing there is? Let's change the question. What is the fastest way to travel through space in the universe? It's c, exactly 299,792,458 meters per second in a vacuum. 1 billion kilometers per hour. Electromagnetic radiation just happens to move this fast. Any particle that has no mass travels at c, without acceleration or any in between. The light that's being released from a candle does not speed up until it reaches light speed. At the very instant of its creation, its speed is c. So why is c, or the speed of light, finite then? Well, nobody knows. Our universe is just built this way. We don't have a smart answer here. So light is a part of a spectrum, an elementary particle that also behaves like a wave, propelled by two perpendicular fields traveling at the speed limit of the universe. Okay, that's nice and all, but what about all the crazy stuff about traveling at the speed of light and time, the twin paradox, quantum stuff, and things like that? We have to save them for another video. For now, let's just be happy that we evolved eyes that pick up waves of information permeating the universe, making us see things that help us to put our existence into perspective.
He says something at the beginning of the video that might be confusing when he said that the photons are created and destroyed. He didn't say energy is created or destroyed. The first law of thermodynamics tells us that energy cannot be created or destroyed, but it can be converted from one form to another. And that's what happens with the photon. The photon can be absorbed by an electron, and then the electron will move up to a higher energy orbital. And when this occurs, the photon is gone. So that's what he meant by destroyed. It might not have been the best term or a term I would have chosen. And then when he said that they can be created, when an electron loses energy and moves to a lower energy orbital, it can release a photon. And that photon was created, quote unquote. But he's not saying that energy can be created or destroyed. He's really saying that it's being converted from one form to another. This next short video gives you a review of the traits of waves.
Waves. One of the first things we need to know about waves is there are two different types of wave. One shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the C waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as a distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
All right. At the end, he relates speed with frequency and wavelength. And we can also relate wavelength to the energy of that wave. And with photons, the energy of the wave is inversely proportional to the wavelength. So what that means is if a photon has a very long wavelength, a very large wavelength, then the energy is low. And if the wavelength is a smaller number, then the energy is higher. They're inversely proportional. And that can come up as a application type question where you would relate the wavelength of the photon being absorbed by a pigment and understanding how much energy also came with that photon. And the more energy that is received with the photon, that can increase kinetic energy and can release a lot of heat. So you want to be on the lookout for questions that imply maybe some kind of temperature change or increase in temperature, increase in surrounding energy. That would be associated with the photons that have the shorter wavelength. And then the photons that could possibly be absorbed by a pigment, if the wavelength is a very large wavelength, then less energy would be absorbed. When photons are absorbed by electrons in the pigments, the electrons move to a higher energy level. So I have several videos that we're going to watch just a small portion of for you to visualize what this looks like.
So this Bohr model of the atom that we know and have sort of known for a couple of years has this kind of dense positive nucleus surrounded by the electrons in different shells that we have.
Okay, so I am fast forwarding it a bit. This YouTube channel, they have a lot of really, really good videos about the orbitals, orbital theory, molecular orbital theory, atomic orbital theory, etc. And he does a good job of showing how electrons, in order for them to move to a higher energy level, the energy that they absorb has to be the exact right amount of energy. If it is not the exact amount of energy necessary to move to the next orbital, then that energy just keeps going. It doesn't get absorbed by the electron. And in terms of photons, any photons that cannot move an electron to a higher energy level would just go right past the molecule, and we would still see those wavelengths of light. However, if there is a photon with the exact right amount of energy to be moved to a higher energy level, then we would not see that color anymore, because that photon is now in the electron in the higher energy level. So we're gonna just watch a little bit of this and pay attention to these energy requirements for the electron to move up to a higher energy level. And then also notice that if it is a lot of energy, the electron can be promoted to a much higher orbital. And if the energy is a certain amount of energy, the electron can get so much energy that it could actually leave the atom completely. If it does get promoted to an orbital of higher energy, when that electron loses the energy to go back to the ground state, it doesn't have to be that same amount that was absorbed. The electron can release just part of that energy and then release a photon of a completely different wavelength, and it would be a completely different color. It's really cool. And then it also can release energy as heat. It doesn't have to be a photon.
In maybe one of the simplest elements, which is hydrogen, which is effectively a proton surrounded by just one electron. And this electron can exist in maybe the innermost shell, which we call the ground state, which is this one over here, or it can move up through various different energy shells until it escapes, and then we have this effectively a positive hydrogen ion, or also just known as a proton. So we're going to really consider that. You have the first energy shell down here where n is equal to 1, so n is just a number, and then we've got the shell 2, 3, 4, 5, all the way up to the outermost shell, which is going to be effectively the shell which is a bit like infinity. And because each shell is an energy shell, they also have a corresponding energy. Now the one at the outermost is 0, so anything beneath that has a negative value. And the values here I'm going to measure in electron volts. So 1 electron volt is 1.6 times 10 to the minus 19 joules. And I'm just going to fill in the numbers for the different shells that we have here. So perhaps by looking at the energy levels for hydrogen, we can maybe think about one of these electrons as it moves from maybe the ground state up to the next energy level. And what happens is it will absorb some energy, perhaps from photons, perhaps from being heated up, or perhaps being excited in another way. And it sticks at this energy shell here. Now it doesn't really like being there. It's not as stable as being back in the ground state. And what it does, it then loses a certain amount of energy. And we've had a change in the energy of that electron. And what this does is, as the energy is released, it's released as a photon of radiation. And we've seen in the last video that the energy of a photon is equal to hf, which equals hc over lambda. And what that means is as the electron drops energy levels, it emits a certain wavelength of radiation. Each atom in the periodic table has its own certain series of energy levels, and it really depends upon the makeup of the atom or even the compound that it's in. And what we find is that there are certain distinct energy changes associated with various elements, and this is the same everywhere in the universe. And what we can maybe look at is the energy change from E2 to E1, which is maybe done some flame tests, perhaps with G6.
So here he shows all of these different transitions that are possible, and each one of these would have associated with it a particular amount of energy. And he also mentioned that this is the basis for the Atomic Absorption Lab that we do in chemistry. You have this little spectroscope, and when you look through it, you see certain lines of color, and those are actually the photons that are released between these energy levels and orbitals. And each atom has a different set of energy levels with their own value. And the reason they're all different from each other is because each of the elements has a different number of protons and neutrons than all the other elements. So their exact energies are different. So they have that signature release of different colors of photons, which is also really cool. All right. In this second video, he goes into more detail. And I have just a screenshot of the video showing how there are really so many choices for the electron when it absorbs energy on the type of radiation it can release. It doesn't have to be visible light. It could be IR, UV, etc. And so I have this link here, and you can watch it. It's from the same YouTube channel. They've got a lot. It's called Physics Online, and he does a really good job making these really difficult concepts much easier to understand. And then if you are really, really interested in it, I even added an even more complex video about it, which it is really fascinating. And he goes into more detail about actually calculating the amount of energy that is necessary or that is released. And he explains more the concept of these types of energy diagrams. And then he even goes into more detail about the amount of energy that when it's absorbed, the electron leaves the atom altogether, and that would be the ionization energy for that particular electron. So I will leave those there for you. All right. I think what we'll do is stop here, and then I'll pick back up in the second video, and we'll start with the Engelmann experiment.